Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering the Module 3 Inquiry Question 1 exam question, which is the 2013 Independent 11 Question 20. So, first part of the question, it says, with reference to the direction of energy transfer through a medium, distinguish between a transverse and a longitudinal wave. Okay. So we need to firstly consider the direction in which the wave is moving, and then we want to distinguish the difference between a transverse and longitudinal wave. Okay, you could write this as a full written description response. So we know that and I'll do some labeling here, with a transverse wave, the medium oscillates perpendicular to motion, so perpendicular to the wave's motion, while this one oscillates back and forth. Okay, so that's kind of, you could write it as a description. What I'm going to try and do, I'm going to try and show this as a diagram. Okay, so I'm going to use this as the 0 point here of my wave. You can see the wave. I'm going to say the direction of my wave is going in this direction, and then I'm going to do the exact same thing, but this time for a longitudinal wave. I'm going to point them like so, and then these components here. Okay, so there's that. So this is for my transverse wave. This is for my longitudinal wave. Just to make it clear for everyone, I'm going to use a different color. Okay, so we have our particles oscillating up and down. So if we have a particle, it will oscillate up and it will oscillate down like that. So in terms of the medium, we can say that the particles in medium will oscillate perpendicular. That's the sign for perpendicular in maths, to the wave's motion, while as this one here, we have the particle moving backwards and forwards. Okay, so particles in this medium oscillates backwards and forwards to the wave's motion. Okay, so that's our distinguishment between the two types of waves. Alright, let's go to the next question. B, it says we have a ripple of an amplitude of 4 millimeters, a frequency of 1.5 on a lake. On the axis below, draw a label diagram or label graph to show the variations in displacement with variations of time. So this is going to be our amplitude, or let's say our displacement, sorry, amplitude is the wrong word to use there. If our amplitude is going to have a maximum of 4 millimeters, that means the scale we're going to use is 4 mm. And then we have the time, and that will be in seconds, because it's hertz we're dealing with here. Firstly, let's work out the period for one wavelength to occur. and that'll be 1 over frequency, which is 0.5. In our calculator it goes, and it's around about 0.667. If we round it off, it would be 0.6 repeater if we just let it as it is. So that's what we have. So we want to draw a graph to show the variation of displacement with time. From this, it doesn't seem to be too concerned of how many periods we draw, so that's always a good thing. Let's say this is 2, this is 4, this is our 0 point, this is -2, this is -4. Okay, so the next part is just to get the correct time frame in. So what we can have, the period 0.6, let's do here, we'll call that 0.667, or let's just call it 0.67 just to round it off. And then the next point where we'll see another one, 1, 2, 3, 1, 2, 3, 4. Over here would be around about 1.34, around that margin there. Let's draw in our graph. Okay, so if we're going to see a wavelength at 0.67, we'll expect to reach the maximum at this point here, and then it comes down. That's half a wavelength already done. Come down and back up. Okay, and there's that. And then we draw a second wave. And there we go. Oh, overshot it a little bit, but that's kind of what you're aiming for. Okay, so that's how you could use the period and frequency formula to work out the wavelength or the time for one wavelength, and then this is how you can display this on a graph to show variations of displacement and time. Hopefully you enjoyed this video or found it helpful. If you do, please give it a like to support other videos coming out in the future.